Cool. So I saw all the labs were submitted. Good job. I will have that back to you. I'll have the grades back to you by Tuesday. Additionally, when I read over your challenges, what I'm going to do is I'm going to make edits to the lab one, the write-up that I'll be giving next year. I'll be posting that for you guys on Tuesday as well, so you can see how your comments have improved the course. Also, I do want to publicly congratulate Mr. Kevin Lindemeyer, successfully passed his PhD qualifying examination. So, outstanding, good job, Kevin. So, okay, so let's get back to adders. So let's see. I want to edit PDF comment. All right, so we just briefly discussed how adders works. You have your two XORs. We've actually done problems in the past where we have to split it in half and split it in half here, and to be able to figure out where the short is. We also discussed really briefly the actual .v file. So you have your inputs labeled, you have all of your inputs, and you have your XORs, and you have logic, and I showed you different ways of doing it. This is from the textbook. This is an example of a dual rail full adder, where it's A and A bar, B and B bar, and carry in bar. And then this is sum, and this is carry out. And I showed you an example of the layout here. So what would happen if you somehow shorted your cell to ground in one place? You'd actually get multiple errors, and it would actually be problematic. So this is why I wanted you guys to be aware of how that actually works and why I'm harping on it. So for some of the feedback I got from the labs, remember how I harped multiple times, look into the technology file and look at the name that they're using. I think 2 or 3 groups email me, why is it not compiling? And I say, I'll change it to AOMI6P or change the file to P, and then it will run, and then it ran. So I promise I am attempting to try to save you guys as much time as possible. But so you'll be doing this in the lab. You'll actually be taking a file of an adder, an ALU, and then the data path, and you'll be synthesizing it down and being able to see it rendered using the synthesis tool to actually give you a metal layout, a CMOS layout. Full adder, the ripple carry is you just have carry in, carry out. We discussed, I think this is where we ended last time, 8.16, this discussion of run times. And then what we wanted to do today is we want to talk about what is this carry look ahead, and what does that mean? So ripple carry is slow execution time, big O of n, but reduced area. It only has 32, if it's a 32-bit machine, it'll have 32 full adders. If it's an 8-bit machine like the one you'll be synthesizing in your lab, it has 8 full adders. Next, carry select. What we're doing is we're cutting it in half here. We assume, so the carry is either going to be 0 or 1, right? So what's going to happen is we have 2 16-bit adders where we assume it's 0 or we have it's 1. It figures out that portion of the solution and then uses the carry from the first part as a multiplexer to give you the last 16 bits. So the goal is to try to cut down on execution time, but the trade-off is increased area. Now, this carry look ahead, it uses more and more different ways of propagating the carry or generating the carry, meaning it's actually trying to predict what the carry is going to be in advance of it getting there to try to make it run extremely fast. But you also have to worry, you get a lot of area overhead, so we have to worry about 3 specific things called propagate, generate, and kill. So propagate means that you're actually taking a value and propagating along if it meets a certain logical condition. Generate, you're actually predicting what the carry should be, and then kill is what happens if your prediction is wrong. So we'll be talking about that in a split second here. So carry look ahead has the best execution time, big O of log of n. So it's going from big O of n to big O of log of n. So if you have, let's say it's 32 bits, right? So it'll take 32 time slices, where log 2 of 32 is 5. So that's our goal, right? Try to cut this down as much as possible. However, n log n, so that becomes 32 times 5 instead of just 32 of area overhead. So there's actually, so we're going to discuss how these are generated and ways to kind of mitigate this area overhead. The three carry Lookahead adders make 3 calculations. So these are the 3 I just talked about. And this is how it's going to be done. Generate is C out is 1 independent of C, basically meaning so the generate value is going to be A and B. The propagate is going to be C out is equal to C, the carry in. So that means just A XOR B. So that now normally the carry out would be XOR C in, but here by leaving that off, that makes it equal. And then the kill was when C out is 0 independent of C, so that means kill is equal to not A and not B. And I'm going to scroll up just a little bit to the top here. Okay, so basically with Koch-Stone adders, you see here, this is a 4-bit Kogi-Stone adder. So this is Peter Kogi and Gerald Stone. The Koch-Stone adder is a parallel prefix for form carry Lookahead adder. It generates carry signals in big O log n time, and it's currently considered the fastest adder in design. Peter Kogi is also, for those of you who've taken 385, Peter Kogi is also the guy who invented pipelining. He wrote and he's also written the fundamental textbook for pipelining. And I actually, I'm going to shamelessly name drop here, but I actually had lunch with him 4 years ago now, and we went to his office, and he had the chip where he made the first pipeline circuit just on his desk. He made it when he was working at IBM, but we all sit there like some genius came up with this, and it's in a museum. And no, it's just there on his desk, like it's a picture of his kids or pencils or so. I found that rather amusing. But the general idea is here we have our 4 kind of main adders, right? So the way it works is you're outputting propagate and generate, carry in, and SI here, so sum and carry out, right? And then what you're going to be doing is, as they're running in parallel, see how it kind of cuts across there instead of doing 1, 2, 3, 4? It actually goes by factors of 2, right? So this one's going to go 1 and 1. So next 2 are going to go 2 over and 2 over and so forth. So here, this is propagate and generate is on the output. So PNG is this output. So here, the inputs to the yellow are PI and GI, and then PI previous and GI previous. So as you can see, it's contributed here as well as from this calculation on the output. So what's happening is it's calculating all the propagates, and then by a factor of log of n, it's taking those previous values and using those to calculate out. So if this were 8, what would happen is there's going to be a third row. So this would be 1, 2, 3, be 1, 2, 1, 0, and then they're going to propagate out. And the reason why there's only 3 rows is because they're going in log. So it's going to be 1, 2, 3. This one will go 1, 2, and this one will just go over 2, right? Those are 4 and then 2. That's what I meant. 8, 4, and 2. So, and then this one's here 4 and 2, and then this one right here will just go over 2. And that's how you generate and propagate. So what's happening is you're generating a specific value, and then you're going to propagate the values over in a factor that increases their probability of log of n. So what happens is there's 3 calculations for each bit, right? So you got propagate, generate, times propagate, generate, times propagate, generate. Now these all have 0 here, and then you're going to use this to calculate each one. So the first n value, so let's say this was a 32-bit adder, so I'm sorry, log n values. So the first 5 would have 5 of these green propagate and generate, 4, 3, 2, and 1. And so that objective means that and they all come out at the same time. If you remember in 385, we had to take great care to ensure that timing was proper when we were doing those VHDL projects. One of the benefits of coding at this level is that these are all ands, right? You have ands, so on. You just have to manage the inputs properly. So therefore, it's guaranteed to all come out at the same time. But the challenge is this becomes massive in terms of area. So these are all the calculations for a 5-bit adder here. So let me show you these two TGOs. And so this is a 16-bit adder here, right? Where we have a lot of area overhead. N log n, here we had all of these values, and then it's n, 2, 3, 4, and 5. So that's where the n log n comes from. So you're getting a lot of area overhead. However, we can cut down the number of carries by using a concept of sparsity. But when we read radix first, radix of the adder refers to how many results from the previous level of computation are used to generate the next one. So here, right, here we have 1. It uses this level and this level, right? 1. Does it use this level? Yep. So it uses 3 previous. So it's a radix 3 adder. Sparsity is how refers to how many carry bits are generated by the carry tree, right? So here, we're generating carry bits. If you did this, you'd be generating. If you see that there's a significant reduction in the number of carry bits generated. So the trade-off is it runs a little slower. So you're gaining a little bit of area, you're improving over your carry select adder, but you haven't gained the full value of the the full area overhead. So does this make sense? I want you guys to understand the general idea behind full adders and how they're worked and how you can actually use them and try to make them run fast. So your trade-offs are area and performance. So does anybody have any questions on that? All right. So the next thing I want to cover is SRAM. So if those of you who've had me before, I harped on this concept of SRAM where the registers in MIPS use dual read, single write SRAM. So why did they use dual read, single write? Come on, you guys know this. You know this. Hit R-type instruction. What are you doing in an R-type instruction? You need to jog your memories because you guys are about to read MIPS. What's that?
Loading from registers.
Mm-hmm. So it's specifically, recall the definition of R-type instruction. You're taking values from 2 registers, performing some sort of operation in the arithmetic logic unit, and then storing it in the 3rd register. So if you recall, if you have an instance where j equals I plus I, let's say that's the code, right? So I need 2 copies of this value to go into my arithmetic logic unit, right? Well, how do I get 2 copies? Read it twice. Dual read. So first we're going to discuss the fundamentals of SRAM. So the SRAM here this is known as a 6T SRAM cell. So here you can recognize this is an inverter. This is an inverter here. So the other way of drawing this out is you have your word line, you have bit and bit bar, and this goes to an NMOS transistor. This goes to an NMOS transistor, and this is actually an inverter, right? And this is an inverter back. So you have your loop, and your loop is how you serve the information. So you have your VDD and ground, you have your PMOS. The output of this inverter is tied to the input of the next inverter on the left. And likewise, the output of the inverter on the right is tied to the input of this inverter. So that's how you get your loop at the CMOS level. Bit and bit bar control your source. Your drain on your source on your NMOS transistor. So you have word line and then bit and bit bar. So that means bit and bit bar are going to be the opposite. And so I'm going to describe here what's going on in the next little spiel here. So if you have an NMOS transistor and you put a 1 on there, right? You're putting a 1 on the gate in order to have a 0 flow through on the output, right? So what's going to happen is bit and bit bar, so let's say word is 1. Now, means bit and bit bar, one of them is going to be 0, one of them is going to be 1, right? In the opposite case, the other one's going to be 1, the other one's going to be 0. So that means this transistor will create a flow because the NMOS is a good conductor of zeros. This one won't because it's a poor conductor of 1s. And so this right down here is an example. Actually, let me formally read this. The 6T SRAM cell uses pre-charge and write phases to store and save data. So for a read, what's going to happen is you're going to pre-charge both bit lines high. So this is pre-charging. We're going to have bit and bit bar are going to be both 1. And then you're going to turn on the word line. And then you're going to pull down one of the bit lines. One of the bit lines will be pulled down by the cell. So pre-charge means I'm turning them both on. It's not like the instance where we have a flip-flop and Q never, ever, 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 ever equals Q naught. Bit and bit bar initially high, and then by the value, when the load line is turned on, one of them is going to be pulled down. So for example, if A is equal to 0 and A bar is equal to 1, the bit line is going to be discharged, and bit B, bit bar, is going to stay high. Right? So here's your value for bit bar. You turn A bar goes to 0, and then the word line goes up, right? So this is the layout of the A bumps up slightly, so that means A must not, so the thing is for the read stability, so this is an example of a read. We've pre-charged, there's a value there being stored in the inverters. We pre-charge the lines, and based on the current value, it's going to pull one of the lines down. That value is going to bump up slightly, and that has a lot to do with energy dissipation. And while you're doing that, you have an instance where, since you have 2 inverters and you have 2 PMOS and NMOS transistors, there's going to be a slight instance where it's going to try to pull up because you haven't fully shut them off at the same time. So but it's eventually being pulled back down, as you can see. So you have to, it must not flip. If it flips, that means your transistor sizing is wrong. Now here's what happens with the write. So what happens with the write is you turn on the word line, and then the bit overpowers the cell with the new value. So you turn on the word line, like I actually just described a write previously. For example, if A is equal to 0 and A bar is equal to 1, and bit 1 is equal to 1 and bit bar is equal to 0, you turn on your word line. Now you force A bar low. I can show you the little dot diagram that's from the textbook. So A bar is forced low, and then A is risen high. So what you have now is you have now changed the value of the cell. So I should say what they mean by A and A bar is the values of the inverters. Okay. So this would be A bar, which correlates to B and bit bar. As you see, A bar goes down with B bar, and A, and bit goes up with A, right? Now this last little note, you have to overpower the feedback inverter. What that means is for a little while here, one of the reasons you have this delay between word and A is because there's still feedback going on between the inverters. So when you write, you actually have to not only write to them, but you have to change the value that's being looped back and forth, right? You have to physically overpower it. So there's some interesting transistor sizes. Your NMOS transistors are going to be your transistor size, particularly for one of the transistors, it has to be on while PMOS is off. So you're going to get like 12 and 6 for both of those. There are going to be some interestingly large values there. Does that make sense? That's kind of like a cursory overview of how it works. So at the CMOS level, let me see if I can. All right, so here I'll just read this out and then I can show you. So on the left is a CMOS polygon level. The cell size is critical, so it's 26 by 45 lambda. However, in industry, they try to make them even smaller because they're trying to compress size because area is often important. But for your scalable CMOS, your lambda-based design rules that you're using in this course, it's 26 by 45. In the middle, I've presented the stick diagram. And on the right, I've presented a stick diagram with 4 CMOS transistors, 4 SRAM cells. And then this is an example of using the layout overlap that we discussed in section 7 to reduce overall area. So now that you're aware of how the layouts look, you can see inverter 1, inverter 2, you have bit and bit bar, VDD and ground. So you see the loop here. And then you use the word line and bit bar to read and write. So you pre-charge the bit and bit bar, and then raise the word line in order to read. And then for write, you're gonna raise the word line when you have the opposite value. It has to overpower the value in the cell, and then go to steady state. So this is the stick diagram. So if you were given a stick diagram, you draw this out. You can see your first inverter. You can see your second inverter. You can see there's different metals now. So we have purple, the same as VDD and ground in terms of color for metal 1. You have your poly, right? And your poly is here. You can see that the poly from the output, the input here is the same as the output of the inverter. So this is where the loop comes in. The loop, I can actually draw the loop. So loop goes here. Right? There's actually 2 different paths, and the reason why there's 2 different paths is 2 different values. And then last, but certainly not least, by sharing VDD and ground, by sharing VDD and ground, you can actually use that to reduce the area of 4 separate SRAM cells. Now, common mistake, people are trying to build it up and they don't size it properly, so they'll actually have this separate over here. So a lot of designers will waste a lot of area by not considering that, hey, I can use this layout overlap and use that tool to test it before I merge everything. Here now you've reduced a lot of area. It still works exactly the same. And you can, especially when you're trying to consider how to make it as small as possible, these kind of techniques, especially for memory, become extremely helpful. If you remember back in section 5 when we talked about wires, and particularly if you remember, I presented a problem where like 85, I believe it was 85% of the wires go to memory and then 15% are in processing. And we were calculating the power consumption based on the switching factor. So these have lower switching factor, like 0.06, whereas the switching factor on average for it was 0.5 for processing elements. And we also know that the power consumption of wires is directly related to the length, right? So by using layout overlap, especially in memory elements, you can significantly reduce the power consumption of the chip because you're reducing the length of the wires and you're still getting the same results. Does that, hope that's a good combining concepts question, not question, but it's a good combining concepts concept. So does anybody have any questions on this before I move to dual read, single write? All right, so I just wanted to show you real brief. This probably seems rather intuitive. So I have word A and word B, so you're just adding another line. Word B goes to this transistor, word A goes to this transistor. So you're just adding you're just adding a second wire to it. And you set word A high, you're trying to read it. Word B is low, you're not reading it. You set them both high, then you're reading the value out to both outputs. So dual read, single write SRAM uses 2 word lines to indicate a read. This indicates that it can be read twice at the same time. And so you'll need that, so we're about to start talking about the MIPS data path. So that's an important concept to understand. Okay, does anybody have any questions before I move on? All right, so MIPS multi-cycle implementation. So for those of you who've done this before, basically the idea is single cycle, you add 5 stages, then you add 5 stages for timing, right? So pipelining, what it is you have your 5 stages, but then it starts a new stage because there's a stage in between, right? But the reason why pipelining can be difficult to implement is because you have to worry about pipeline hazards, you have to worry about significant area overhead, you have to have a data hazard control unit, and you have to worry about propagating all of your control signals throughout the entire circuit through each register. So you have registers in between instruction fetch and instruction decode to execute in memory, and write back. And also you had to do all 5 stages. But for example, in R-type instruction, this is a good example. We'll be going over this FSM later today. In R-type instruction, we'll start with you fetch the instruction like normal, then you decode the instruction like normal, then you're going to execute and get everything from the registers, put into the arithmetic logic unit, but you're not using the data memory, right? You're taking that value from the arithmetic logic unit, circumventing the data memory, and just storing it into the registers, right? So but in pipelining, you have to just wait while the data memory stage is being done, right? So that becomes problematic. So if you're in a bind where I need to improve performance, but I have area constrictions, this concept that I'm going to introduce here, the MIPS multi-cycle data path, is actually a very good compromise. Remember, design principles, good design requires good compromise. What the MIPS multi-cycle does is it only uses the parts required in the data path, and if it's not using the data memory, like R-type doesn't go to it, right? For example, load word is the longest instruction because it's going to load the word from the data memory into the registers. Store word is only putting the value from the registers and storing them to the data memory. So there's no need for that last write back stage. And for those of you who haven't learned MIPS, there are 5 stages. Instruction fetch, get it out of the instruction memory. Instruction decode, we decode that 32-bit binary value into an opcode, register values, and which we'll discuss in a TGO here in a minute precisely how that's done. Execution goes to the arithmetic logic unit. It does some sort of actual operation. Data memory, if it's a load word instruction, that means it's going to put the value, if it's a store word instruction, it's going to put the value to data memory, which is our non-volatile slower memory for the cache hierarchy. Or if it's load word, we get that from the data memory, and then we'd be putting it back into the faster registers, which we'd use for faster instructions because we're trying to take advantage of the principle of locality. So that's a very brief overview of 385. So doing this MIPS multicycle allows for faster clock rates, just like pipelining, because we don't have to worry about the specific stages. Different instructions take a different number of clock cycles, like I just described. Functional units to be used more than once per instruction, as long as they are used on different clock cycles, which means here they've combined the instruction memory and data memory into one memory. And we'll discuss how they differentiate a value coming out as an instruction or data. So those of you who've done control signals with me before, if I wanted to determine whether something is an instruction or data, what would I want to call that control signal? For example, if I'm trying to determine the ALU source, right, which I called it ALU source, right? So if I'm trying to determine if it's instruction or data, what do you think it should be called? Let me ask my question again. You guys are making this engineers are spinning it. This is KISS, keep it simple, silly, right? I'm not going to call you guys stupid. If I'm trying to determine the ALU source, and I name the control signal ALU source, right? Like, if I want to determine if I want to read from the memory, the instruction is called memread, right? If I want to write to the data memory, I call it memwrite. If I'm trying to determine if something's coming from the memory to the register, I call it memory to register. So I have a new thing that I want to find, whether it's going to be called instruction or data. What do I want to call that control signal?
Instruction.
There you go. See? I told you the construction. See, you guys, that's engineers. Come on, I got to think of this.
Was that in the MIPS path that we did in?
It is not. That's why I'm asking the question. We're going to be going over it, the multi-cycle implementation today. So since you can combine things, you only need one memory, and we're only going to use one ALU or adder. So for those of you who haven't gone over MIPS, what this means is in the single cycle and pipelining, we had two specific adders in the Datapath to help us calculate the next instruction, as well as we had to add the current value of the instruction plus what's known as the immediate on a branch instruction to determine the possible next instruction to go to. Here we only have one, but we're going to be using a finite state machine for a controller. And the FSM is the important part of your lab report to do this. So we have 5 additional registers. In single cycle, we have 32 registers. So we're going to add 5 here. We call it the instruction register, where this value comes out of the we have instruction register or memory data register. You can see where you're trying to differentiate between things. And we have 3 other registers. We call it A and B. Since we're going to be breaking down into time slices, A and B are your 2 outputs from the registers to control your 2 inputs into the ALU. And then ALU out, we're going to store the value of the ALU out for a clock cycle to be able to differentiate between different types of instructions. So those are the 5 registers added to single cycle implementation. So what are these instruction types? There are 3 instruction types: R-type, I-type, and J-type are registers. Registers used for instructions to perform an operation on 2 register values and then store the result in a 3rd register. So the opcode is a 6-bit value that determines the instruction type. RS and RT are these 2 register values. Let's say we're adding it. So the value, so this 5-bit value is translated into a 32-bit value. That is a 32-bit value, so you have a 5 to 32-bit decoder. So one of them is on. That one value that is on is your line that goes into your dual read SRAM. So if you have 2 values on from 2 32-bit selections, that's where word line A and word line B come in, and that permits your dual read. Then it goes to the arithmetic logic unit. Some operation is performed. In this case, we have selected addition. And then it's stored back into the 32-bit value indicated by RD. So that's our write line. Shift amount, if we're doing a shift left or shift right, we can potentially shift up to 32 bits. Or in your 8-bit data path that you're doing in this course, 0 to 8 bits. More often than not, shift amount will be 0. And then function, which I'll just briefly say, but we in 385 went into tremendous detail. Function different, all R-type opcodes are the same. If you look at this table right here, all the R-type opcodes are 0, and the function values are used to determine or differentiate between different types of R-types. So here, addition and subtraction of the 6-bit function. Addition is 100,000, and subtraction is 100,010. Now I should indicate for those of you in 385, these values that are being used in the reduced 8-bit MIPS data path in this course are different than from the green sheet in 385. So just refer to these. This is why I included this table as a TGO, because you're going to need, in order to complete the add-i's down here, you're going to need this specific opcode in order to be able to complete your assignment. Okay, so you need to demonstrate understanding. So speaking of add-i is an immediate value used for data transfer instructions. So add-i means I have one register and a constant, and the constant is the 16-bit number, and I take it from RS, add it in the ALU, store it in RT. And then jump instruction, we use a 26-bit address. We shift left by 2 in 32-bit because we are multiplying by 4 because 8 times 4 is 32, right? So if I'm shifting left by 2 to multiply by 4, what would the shift be if I'm doing an 8-bit data path? So we've done 32, right? So we have to get from 32 to 4, right? So from 8 to, we have 4 8-bit blocks for byte addressing, right? Which is why we have to multiply by 4. Because a 32-bit requires 4 8-bit blocks. In an 8-bit data path, we only need 1 bit block. And shifting left by 2 is the same as multiplying by 4 in decimal. So what would the shift amount be for an 8-bit value? So if it's 32 bits, I have to shift left by 2 to multiply by 4. So let's say it was a 16-bit data path. I only have to shift left by 1 because I'm multiplying it by 2 because I have 2 8-bit blocks. Right? So now let's go down to the 8-bit data path that you're using. How much do I have to multiply 8 by to get 8? So how much would I have to shift by? 0. Bingo. 0. So the data path is going to be a little different here. So this is the table I want you to include. For this is an example, 2 and 3 is stored into 1. The dollar sign and the value after represents the actual register name. So here it would actually be register 2. From MIPS, we won't have to go into any kind of detail on this, but in MIPS, those who remember last semester, we had like S0, S1, S2, V1, V2, T0. Those are differentiating between saved temporary values and variable values, right? In this case, you could do that, or you could just say $16 is the same as S0, for example. So that's what the notation means. So we have the instruction. So here, this relates to the, so you have your code, and then you have your assembly language and your machine language. So you're trying to translate it down. So you have your register transfer language, which is what this is. So you have 2 and 3, and you're adding it to 1. Don't really worry about this. You don't really need to worry about this that much for the course, other than just for reference. Because in this course, I'm not going to expect you to translate anything from C to MIPS. Yes, Tanner?
Is there a way to use an immediate number?
Correct.
I want to use like 4, not what's in register 4. Oh, okay.
Add-i. No need to say sorry. It's a good question. You're thinking a little ahead. So, right. So these are all the R types, and these are the function values. Now make a mental note, because we're going to go over this in a little bit, that the opcode for add I is 001000. Because what you're going to be doing is you're going to be taking Verilog code, and you're going to be modifying it to be able to add to the finite state machine to be able to complete an add I instruction. And I'm going to show you how to do that, and then you're going to complete that for your lab. All right? So BEQ, branch equivalent, it means it compares the values in 1 and 2, and then if they are equivalent, it will branch to the value indicated by the immediate value. So the immediate value is an actual instruction. So let's say typical branch, if statement. If A equals B, right? I'm sorry, A does not equal B. If A does not equal B, you want to do the value inside, right? That means you branch if they're equal. So in this case, let's say you have to skip 7 instructions. In this case, since it's an 8-bit data path, the value is going to be 7. Now, if it was a 32-bit data path, it would still be 7, but then we'd shift left by 2 to be able to multiply by 4 to get to the specific instruction we want to get to. So that means the data path, there's going to be some things from the data path that you saw in 385 that won't be in this one that I'm about to present. And then you have jump. Now, load word and store word. Word is 32 bits. So in this instruction, it's load byte and store byte because you are getting a byte or storing a byte to the data memory. So that's why it's LB and SB instead of LW and SW. And so this is the main J-type instruction. All the rest of these are I-type instructions, which means there's no function. And the reason why there's no function is because the 6 bits that would be a function for an R-type value are taken over by the 16-bit number. Now, the other thing that's important, and you're going to need to bear this in mind in your assignment, is LuOp. So what's going to happen is you're going to send a 6-bit value, the op signal, to the controller. The controller is going to generate a finite state machine, which I'll present to you in a little bit. As part of that, it's going to generate 13 control signals as opposed to 9 in single cycle. One of those control signals is called LuOp. So what's going to go? It's going to go to LuOp, and it's going to take that value plus the 6-bit function and actually determine what should be sent. The reason why this is important is it's 0, 0. Here you've got add. So now your ALU control value is going to be generated from your function, right? So if LuOp is 0, 0, 0, 1, that means, and it doesn't take, let me start this again, just so I'm clear. LuOp is 0, 0, 0, 1. It does not combine with a function. This means it's doing something with an I-type instruction, right? Same thing down here with 1, 1. If it's 0, 0 coming from LuOp, that means we have gotten the 0, 0, 1, 0, 0, 0 from the add I, and goes down and combines. What happens is, instead of 4 bits, it's 3 bits out from the ALU control in this particular data path. And it's addition. If it's 0, 1, it's going to be subtraction. But here they've actually included a sub-I value instruction. If you recall from 385, they took this out and just used 2's complement to reduce that. Here, they just put it in because it's 8 bits, so it's actually significantly reduced anyway. So now, here, if it's 1, 0, this is what the ALU is going to receive if it's an R-type instruction, which means it now uses that plus the function value coming in to determine. So it's going to send out add. So you see how this 0, 1, 0 and 0, 1, 0 here are the same? That means it's going to send out the same value. What's going to be different is what's going into the other inputs of the ALU. We use ALU source, like I just alluded to. If it's an I-type instruction, it's going to use the sign extended immediate value. And if it's R-type, it's going to use this read register 2 value. Read register 2 is that second value that's read from the SRAM out. So same thing with subtraction. So it is also 1, 1, 0, and, or, and set less than are 0, 0, 0, 0, 0, 1, and 1, 1, 1. Set less than is you compare values. If one is less than the other, then you set it to the the other value. You set the register value to 0 or 1 depending on the instruction type.
Are those the only ones we're going to be using?
Correct. Yeah, and in fact, I've gone into more detail. The one that you're really going to be focusing on in your lab is add I. You're going to be modifying. I'm going to show you what's done because you've been provided the Verilog code for most of the data path. And so we're going to be going over what it is. I want you to understand what's going on in the data path. It's important. But what I want you to do is be able to read this, understand this, and then be able to modify it to include an add I instruction. Okay, so, and I quickly wrote what the add I instruction is here. And they have left 1, 1 as an undefined value. So to briefly allude to it, we got time. To briefly allude to it, recall in the pipeline data path that if you issue, or even single cycle, if you issue an undefined value, that means you've issued, the controller has somehow issued an opcode that does not exist. So therefore, you're supposed to throw an exception up to the operating system. And then you wait, and then once it sends it back, you have to store all the values from the register to the data memory. Then once you get the exception back from the operating system, then you take all the values from the data memory, restore it to the most recently good value, and then start the instruction set again. So that's why undefined is important in that table. All right. All right, so let's I want to briefly go over the high-level view of the MIPS data path. So here you have your instruction register and memory data register. So you have values coming out. You have some sort of address that's accessed, and it's either going to be data or instruction. So if it's instruction, it's going to split up opcode read 1, read 2. If it's data, then it's probably going to be written to the register, right? So in that case, that would be a load word instruction. The data path I'm going to show you is going to be in more detail. This is generally the idea of what's going on. On the each of these registers is being powered by a clock. And then once the clock happens, it propagates the value to the next thing to the right. So, which is what I just said here. So you have, so this example, memory write, it's ANDed with the clock, and it won't occur until the write occurs. Same thing with register write. Now, IR write and memory write are controlled by the clock as well. So it's not going to propagate anything over until the next clock cycle. Same thing with ALU. Here, if we're doing this, the reason why we'd be waiting for the next cycle is because we want our types to take 4 cycles. But if this value is being calculated here, that means we've calculated some sort of branch instruction, which means we want the instruction to be done immediately. So it's not going to wait for the clock. All right. So here there are 13 control signals in the MIPS data path. I'm going to zoom in here. Memread indicates where their data will be read from memory. Memwrite indicates where, and for those of you who've taken 385 or computer architecture with me, none of these are going to sound very familiar. Memory to register indicates where their data will be written from the memory data register or from the ALU. So, and I'll explain. So you have memory data register. That's coming from memory. So this instruction is going to be 1 if it's a load word instruction. Or if it's a 0, it's going to be from the ALU. And that's why, the reason why it's 1 is because it's mem to reg. So here, if it's coming from the memory, that means it's load byte. I should grab myself load byte, not load word in this case. So 1, it's coming from the memory. 0, it's coming from the arithmetic logic unit. I or D, which is what you guys named here, indicates where the address is the instruction from the PC if 0, or the destination. Or data. That's data. So it's instruction, it's 0. If it's data, it's 1. So if it's data, if it's instruction, I want it to be 0. I don't want it to be going to the opcode. I don't want it to be going to the register. And the reason why is because if it sends a new opcode, it's going to send out a whole new set of control signals. I don't want it to update the opcode at the controller until I actually have a new instruction. So what's going to happen is it's going to be a finite state machine. Initially, it's going to be 1, it's a new instruction. I'm sorry. 0, it's going to be instruction. 1, it'll be data for all the other times. So it's holding it up, so it's not constantly overwriting. IR write indicates whether data will be written to the instruction register. So you have this instruction register that we just described that's waiting to see whether or not we're going to be having data written to it. Register destination, it chooses whether or not it's going to be an R type or an I type, or whether the destination and address in the register will be moved from the IR or from the MDR. So if you remember, register destination was the input to reg write on the registers in the MIPS single cycle, right? So here it's using memory data, which is the comparison back from the from data memory, or IR, which is coming from the previous register. And I'll show you that in a second. ALU source A indicates whether the first ALU source will come from 0, read data, so that's coming from the registers, or 1, the PC. So this is actually, this buffer is being used specifically to determine whether or not you want to add PC plus 1, right? So we're going to have 4 different options for ALU source B. So the 2 options are, it's either going to be the PC or the first read register value. For ALU source B, so it's a 2-bit control signal. Let me zoom on this a little more so you can see. ALU source B indicates whether the, this should be 1 for this course, not 4. Indicates whether the second ALU source will come from 0, read data 2, which means we have 2 outputs from register. 1, the value 1, so if we're doing PC plus 1, we're just going to the next instruction. And the reason it's not 4 is because you're not incrementing by 4, you're just incrementing by 1. The sign extended 8-bit immediate. Or the sign extended 8-bit immediate shifted by 2. And we're shifting by 2 to multiply by 4. Well, I can show you the whole data path here in a second. 10 ALU-op, we just discussed ALU-op, would define it. Sent to the ALU control determines the value sent to the ALU. The previous table describes those values in detail. Now, the last 3, we use these since it's going to be a finite state machine. We're going to use these to determine which instruction we go to, because we don't want to have something called a control hazard, because we want to know precisely what instruction we need to get to. Quick question, does anybody remember the 3 types of hazards? I already said one of, I already said the second.
Pipeline hazard.
The 3 types of pipeline hazards. We define pipeline hazard as any occurrence in the data path that prevented the instruction from completing 1 clock cycle after the previous instruction, right? And then there were 3 things. A race condition isn't right, but it kind of contributes to the first one. You should say control because I already said control, right? Control hazard is one of them, right? So what are the other 2? So control hazard is we're trying to control how everything flows through the data path, and one of the things that we could have is we have just PC plus 1, or we could have a branch, or we could have a drum, right? So we have to somehow control what instruction we're getting to, and if we don't, we have a control hazard. Now, I'll give you a hint as the one that Coleman just alluded to. Why do we split up the memory into instruction memory and data memory in single cycle? What type of hazards are we trying to eliminate? That's the third one. Structural hazard. There you go. I knew it's in your brain. I promise it's there. So structural hazard is what happens if 2 things are trying to access the same thing at once, right? So if I combine instruction memory and data memory into one memory, I have an instance where I'm trying to get instruction or get data at the same time, potentially. And we use that I or D control signal to eliminate that hazard. And the third one, you're talking about structural data hazards, are particularly in pipelining, what happens if you are trying to complete an instruction where you have not updated a previous instructions calculation of that datum back to the registers yet. And so multi-cycle gets rid of that by completing each instruction, then completing the next instruction, then completing the next instruction, or reducing the number of cycles per the instruction. So those types of hazards are eliminated as well. So in order to get rid of this control hazard, we use these three. PC source determines whether the value sent to the PC comes from the ALU out register, or the 32-bit jump address. Next, we use PC write. It's going to be ORed with this next one. PC write can determine if the program counter will be written to or not. And the PC write condition is ANDed with the 0-bit from the ALU. So remember, we compare them. If it's 0, 1's going to come out. So that's branch. Then OR with PC write to determine if the PC will be written to. And so next, this is the multi-cycle data path, and we'll go over this really briefly. Now, I should note here before we do anything else, you see my friend Indica from the University of South Florida is interviewed with AMD, and he was saying when he was doing his drawings of the data path, they were actually getting on his case for not doing this. See his little clock? So that's the actual symbol for clock. Yes. So I have included that specifically as feedback from people saying this is what they were getting on my case on during interviews.
Even if you're marking it as a clock?
Yeah. Yeah, if they didn't draw it, he didn't draw the carrot, they said they were giving him grief. Don't shoot me, I'm just the messenger. I'm just including that to save you guys trouble.
It makes sense.
Yeah. Well, that's also the industry, like over here, let me, for an arithmetic logic unit, this is the universal symbol for it, right? So the clock, that's the universal symbol for it. All right, so let's go through this data path here. I'll explain what's going on. So this clock from the program counter here, so that's PC, that's getting your value back from what I just described from PC write and PC write condition. So first thing it's going to do, we're going to go here. It has the IORD value. So we actually have feedback, the arithmetic logic unit. Is it the instruction value or is it data? So here, and the reason why we have to make that distinction is because we use calculations from the arithmetic logic unit to determine what the address will be for load byte and store byte instructions. Next, we have a clock for memory. The inputs to the memory are an address, and then we have a data value, also coming from the LU. We have memory, and the output is read data, and I also have write enable on the input here, and also a clock signal. The output of the memory goes to the two registers. Here we have IR write, and here is just this is the one that's going to be going to your data, right? So this is your data register, and then you have your instruction register. So the IR write has a control signal as well. Next, if it's an instruction, here's where the outputs. So 31 to 26 are those, means it's the first 6 bits of your opcode. And also 5 to 0 go in here for the function. 25 to 21, so you had op is 6, RS is the next 5, right? So 25 to 21, this is RS. 20 to 16, this is RT. And to differentiate between R-type and I-type instructions, this register destination value here, 0 if it's I-type, 1 if it's R-type. And this control signal is register destination. And 25 to 21 goes to read reg 1, 20 to 16 goes to read reg 2. The write register, so if it's an I-type, what will happen is the read register destination will be 1, and register write will only update this one. So you can read both of them that all you want, but since we only have one write register in that SRAM, we only need one write control signal. Does that make sense? All right. Additionally, we have memory to register, which is the value coming from the clock on the output, and the value. So here we're determining if it's coming from memory, it's 1. If it's coming from the ALU, it's 0. here we sign extend our 16-bit immediate value to 32 bits. So that says 15 to 0. And then it's sign extended. So here we have a clock value that holds our outputs of our registers. And then what's going to happen is this goes to ALU source A. ALU source A, this value is coming from the program counter over here. And then 1 is just coming from read data 1. Read data 2, after it comes out of the clock, it goes into ALU source B. 0, 0 is read data 2. 1 means it's going to be, we're just incrementing the program counter and using the same ALU, so we're just incrementing by 1. If it's 1, 0, it comes from the sign extended immediate value, which means we are doing a immediate instruction where we're adding the value from the register. So if it's add I, hint, this would be 1 for source A and 1, 0 for source B. And then if it's shift left by 2, that means it's going to be some sort of branch instruction. And we still need to shift left by 2 here because the instructions are still 32 bits. Does that make sense? Just we're breaking it down to 1 for accessing data because the datum are 8 bits long. So it's a bit. It means it's a byte instead of a word. So we have decided our 2 ALU sources. We do the calculation within the arithmetic logic unit. The 0 bit is generated. Then we have our control signal. And then we have PC write, which is we have an and then an or. And then or. And then what's happening, I can show you what's going on here. This will actually come all the way back. And this will be used as the control signal to the program counter. So now we have the output of the arithmetic logic unit. And then we have a clock because when we go into the finite state machine, we're going to circumvent this because we want this value to come out for PC source if we're using it to calculate the next address, right? So let me zoom out here and show you this path. The reason why it's going to circumvent the clock is so if we have PC source is 0, 0, it comes back here and then writes to the program counter. However, if we wanted to write to the registers, we save it on the clock, and then we have it go to 1, 0, and then we can actually go back there again. Or, if it's this way, it's an R-type instruction or an I-type instruction where we're updating the registers like I, and then we use our mem to reg control signal like we discussed before to write to the register. So that's the write data. Okay. Now, the other thing, I've just not described one wire here. So we have our sign extended value, shift left 2, right? And we've used the adder. Now here we have this value here that we've shift lefted by 2, so now we have our value. We can then send that back to the program counter as well. So that's why we need this complicated, well, it's not complicated, it's an AND and OR gate. This is why we need this logic up here. Because otherwise, if we don't have this logic up here, trying to send the value back to the program counter will create, that's our control hazard. These here, that also gets rid of control hazard, and that allows us to do that. I'm sorry, structural hazard. And the data hazards are controlled by clocks. Okay. So, okay, it's 12:06, and the finite state machine is actually part of Lab 3. So what I want you to do, include 8.29, 8.1 through 8.29 for your lab. So the lab is, it should be pretty simple. You're basically just taking the image files and actually kind of rendering them and making minor connections, and then actually building up the data path. In lab 3, what you're going to be doing is you're going to be doing what we're going to cover next class. And I might just make the rest of this section 9. Okay? So so this will be 8.1 through 8.29. So you now understand the data path. Section 9 will be the control, pad frame, tape out, and final circuit generation. Okay. So does anybody have any questions on this before I conclude lecture? No, everybody just wants the lecture to be done. Okay. In that case, you are dismissed.